I'm Virginia Cuomo and from University of Atacama, and today I will talk to you about bar properties in dwarf bar galaxies from Virgo. So what are dwarf bar galaxy? There is not a unique definition. So we are generally speaking about galaxies which have stellar masses between 10 to the 7, 10 to the 9 solar masses, which means that are less massive than the Milky Way. And these objects are very common in dense environments such as clusters and groups. And they present various characteristics in terms of stellar rotation and hidden disk features. For example, here you can see the sample of dwarf galaxies analyzed by Riese et al. In 2013, where they measure different, a wide range in rotation from the stellar velocity map. But what we are most interested in here are disk features such as bars. And here you can see from Michel et al. 2021 that it is possible to identify bars and or spirals by performing an unsharp mask of the images of dwarf galaxies. In Virgo, for example, bars and lenses are present in almost half for the dwarf sample galaxy. But these structures are very difficult to be studied because these galaxies are small and faint. So what are the properties that we need to define to characterize bars? So we need to define three main properties. Two are coming from photometric analysis, which means analyzing the images of the galaxy, and these are the bar radius and the bar strength. In particular, the bar radius measures the extension of the stellar orbit which support the bar, and we have different approaches that have been developed in literature to measure this quantity. And as Sol already told us, bars can be associated to other components such as rings or spiral arms, so it is very difficult to catch the ages of the structure. The bar strength measures the contribution given by the bar to the galaxy potential, and it is very useful because it allows, for example, to distinguish between a strongly barred galaxy from a weakly barred galaxy. But maybe the most interesting and most important property of bar is the bar path speed, which is the angular frequency of the bar rotation around the galaxy center of the galaxy center. And to measure this quantity, we can apply the Tremaine-Weinberg method, which is a direct approach based on this simple equation, where the bar path speed is related to these two quantities, which are the photometric and kinematic integrals, which are defined as the luminosity-weighted average position and line-of-sight velocity of the stars, both measured along apertures which need to be located parallel to the disk major axis. If we measure these two quantities in different aperture and we plot kinematic versus photometric integrals, we will get a linear correlation, and the slope of this line is directly related to the bar path speed. Despite this simple formulation, this method requires both photometric and spectroscopic data, and also it requires strong, it has strong restriction to identify the target that it is suited for this analysis. The bar path speed is usually parameterized by the bar rotation rate, which is given by the ratio between the circular velocity of the galaxy and the bar path speed and the bar radius. So we need both bar path speed and bar radius to define this bar rotation rate. And this allows to distinguish between fast and slow rotating bar. In particular, fast bar has a bar rotation rate between 1 and 1.4, while slow bar has a bar rotation rate larger than 1.4. But why are important these properties of bar? Because they can give us information about the bar formation scenario. Bar can form through internal instability, and this is expected to lead the formation of a fast rotating bar, while also interaction can trigger bar formation. But in this case, the bar is expected to be slow rotating. Then during the evolution of a bar, the bar evolves by exchanging angular momentum with the other galaxy component. And in this way, the bar radius and bar strength increase, while the bar pattern speed decreases. So an evolved bar is expected to be slowly revolved. And finally, also the dark matter content in the central part of the galaxy may play a role, and in particular may slow down the rotation of the bar through dynamical friction. So studying the bar properties, and in particular the bar rotation rate, is crucial to understand the bar formation mechanism, evolutionary stage of the bar, and also dark matter content. Here in particular, we are interested in understanding which is the role of the environment in triggering the formation of the bar. So why do we want to study dwarf barred galaxies? Because they are expected to host slowly rotating bars, because of two reasons. First of all, because these galaxies are expected to host massive and centrally concentrated dark matter halo, which may have efficiently slowed down the bar during the evolution. And also because these galaxies are small in mass and live in dense environment, so they are prone to suffer for interactions, which may have triggered the formation of the bar. Unfortunately, there is only one Tremaine-Weinberg application performed on a barred galaxy, and here you can see the bar path speed estimate that was performed by Corsini et al. In 2017. And this is the case of NGC 4431, which turned out to host a fast rotating bar. However, the bar rotation rate is associated with a very large error, which does not allow to give a strong conclusion about the formation scenario of this bar.
Virginia, you have 5 more minutes.
Yes, thank you. So what we are trying to do is to measure the bar properties in a small sample of dwarf barred galaxies that are located in different positions within the Virgo cluster. Here you can see in red points, the red points show the location of our sample of galaxy. They are dwarf and they are barred except for one that need to be excluded. So here I will present you the results for one object which turned to be very interesting and very peculiar. And it is the case of the dwarf XI 3167. Here you can see the MUSE reconstructed image, while the white contours show the isocontours of the galaxy. And as you can see, this object is hosting a bar in the central part of the disk, which has an untypical triangular shape. And this is what we interpret to be as a loop-sided bar, which means a bar that has an asymmetric shape and it is a little bit off-centered with respect to the disk. This galaxy has been recently accreted onto the Virgo cluster. We measure, here you can see, we measure the stellar kinematic, stellar velocity, and stellar velocity dispersion from MUSE data cube using the GIST pipeline, and we recover from that the circular velocity of the galaxy, performing a simple dynamical modeling. And then we apply the Tremaine-Weinberg method, defining several apertures located along the disk major axis, from which we recover the bar path speed of this bar. We also perform a photometric analysis using a Sloan image. Here you can see the radial profile of the surface brightness of the galaxy, position angle, ellipticity, and B3 parameter, which measure the asymmetric deviation from the ellipse shape of the XI FoF. And we can see a large value of this B3 parameter in the bar region. We also perform a Fourier analysis from which we decompose the light of the galaxy into a Fourier series. And here we can see the radial profile of the different Fourier component. An M=2 strong component is associated, is telling us that there is a bar in there, but also strong odd components are present, telling us that this bar is loop-sided indeed. We measure the bar rotation rate, which lies in the slow regime. And given all our analysis, we could conclude that in this case, the formation of this bar could be triggered triggered by interaction. Some preliminary results from the entire sample. Here I show you the results coming from the literature of BART galaxies analyzed with the Tremaine-Weinberg method. We have different properties of the bar radius, bar strength, and bar pattern speed, and the points are color-coded according to the bar rotation rate. And I overplotted with the black stars the results for the sample of dwarf galaxies analyzed here. And as you can see, dwarf galaxies seem to host slow and weak bars, which are rotating slowly. So from this, we will try to understand better which is the role of the role of the environment triggering the formation of this bar. So I conclude here giving you the summary, the references, and thank you for the attention, and thank the organizer to allow me to be here. Thank you.
Thank you, Virginia. We think. Is there any question? There is one question over there.
Hi, Virginia. This is Karina Zemesca from the audience. I was very interested on the MUSE data you have. Have you looked at the stellar populations? I wonder if these are perhaps younger bars.
Yes, thank you for this question. Of course, it is very interesting to study the stellar population for this sample of galaxy, and indeed we are doing this. So I don't have, I just have preliminary results. So for this galaxy, indeed, the bar look younger, but we will perform a better analysis to have a better idea of the stellar population properties.
I'll be interested in talking with you further to know about the masses and things like that. Thank you very much.
Thank you.
Is there any other question in the audience? If not, I have a very short comment. Or could you infer or some regarding this relation between the dark matter towards the central region of the dwarf in relation with the slow pace of the rotation of this bar? Have you any estimate up now, or of the dark matter content that should be there in some cases, or not yet?
Yeah, this is a very interesting question. Actually, we don't have an estimate yet because we might need to perform a dynamical modeling of this galaxy. And unfortunately, dynamical modeling for BART galaxies are still under debate, let's say. So in the future, we will be able to model them and, of course, estimate the dark matter content and compare it to the rotation rate of the bar to see if we can infer some conclusion.
Okay. Okay, we thank Virginia and we move to the coffee break.
Thank you.